Okay, let's start today's seminar. Today's speaker is Ramon Winterhalder, and he will talk about MadNIS, jury importance sampling. Please start.
Yeah, I'm very happy to be here and give a seminar before the school next week, where I also give lectures on machine learning for particle physics. While next week I will rather talk about basics of machine learning. Today I'm going to talk about my latest research of how you can apply machine learning techniques in order to improve particle physics simulations. And this talk is mainly about MadNIS, which stands for MadGraph Ready, because I'm working with the MadGraph people, and
I'm so sorry. Yeah.
and neural importance sampling. What this is, I will explain you in the talk. Since we have a lot of time and there are not so many people, I encourage you, whenever you have a question on the way, stop me, ask it, and then we can immediately solve that, and not just in the end. Sometimes it's easier if you ask the questions while I'm talking. Okay. Now you
maybe tracking here.
No, I think you pushed somewhere. Can you push on this?
Sorry.
Yes.
Okay.
Okay. So the plan of attack is, first we're going to shortly introduce why and where you can use machine learning and particle physics in general, and also in specifically in my application. And then starting from this, I'm going to introduce the MadNIS framework in its basic functionality and also additional features. And in the end, I will come to a summary and further discussion, if you like. Right. So the question I can ask is, how can machine learning help in particle physics? So the LHC analysis, oversimplified, how I imagine it in a nutshell, looks like this. So on one side, you have the nature, which of course needs somehow being measured, which is where our experiments come into play, where we measure a lot of data. And in the end, we have some reconstructed detector level observables. And on the other hand, we have some fundamental theory, and our best guess or our best approximation right now is the standard model. And then, of course, we need some way in order to translate this pure mathematical thing into a form which you compare to our measurement, right? And of course, what we need for this is a simulation which exactly translates this, let's say, Lagrangian-based theory into something which is also on a detector level. Once we have this, we can essentially do pattern recognition, compare these things, and then either just confirm standard model or hopefully in the future find new physics, because that's what we're interested in, right? Find new dark matter, explaining neutrinos, stuff like that. Okay, the question is, where in this, let's say, oversimplified picture, can you use machine learning to help? And there are actually various positions and possibilities. On one way, you can, for instance, actually use machine learning in order to improve the design of the experiment. I'm not an expert on these because I'm not an experimentalist, but there are a lot of approaches of using, let's say, machine learning driven ways of how do you have to construct the experiment so that you perfectly contain all the energy and stuff like that. And of course, once you have the measurement, there's also a question, you could record and you have way more way more interactions than you can actually measure. So there's always some triggering involved because you cannot record everything because it's just not possible. So the question is, and right now it's a purely, let's say, well, human designed trigger on how you throw away points and which you keep. So the question is, can we do this better? And one idea of doing this comes under the, let's say, name of, let's say, using anomaly detection techniques. And I will actually talk about that next week. So if you're interested in that, come to my lectures next week. Then even if you have your data, sometimes you need to be careful and do something like data curation, which means calibration, fix stuff like that. And then, of course, on the other side, on the theory side, we're also interested in using and improve the things. So we, on one hand, these simulations are very expensive, both computationally, but also in manpower computation expensive. So how can we do this better, let's say more precise and also faster? Because Every one of us has a certain time for doing his PhD. And if the things take longer and longer, at some point we will not finish our projects in a PhD, which might be problematic for us to get some positions in career. And also in a general statement will take a lot longer time to find new physics, right? And then of course, in principle, you can also inverse this simulation, which means how can I deduce from some detector level information back on a fundamental theory? This comes under the name of parameter estimation, unfolding, or matrix element method, which I will also talk about next week. Today, I will purely focus on this small bit, if you wish, but it's, on my point of view, already quite interesting. So I will only want to talk about simulation and how we can improve them and make it faster. And the question is, in order to understand where we can use machine learning methods, we first need to understand how do you usually simulate LHC events? And if you just look at the picture, then you have something like this, where on one hand, you have the hard process, which is a thing we usually can describe by quantum field theory. But of course, these partons which are scattering coming from something like a proton, which means there's also a lot of soft stuff going on, which we can describe with QCD, but of course it's not perturbative QCD, so we need some soft description for this stuff. And then in this hard process, that's this, let's say, where we expect the new physics to happen. And then we also have a lot of, further on, a lot of soft stuff going on, like showering of QCD stuff, but also QED. And in the end, of course, we know we have confinement, which means all of these shortly asymptotically free particles need to be back into something, so we have hadronization. And then there's this huge big thing out of here, which is a detector. And all of this needs to be properly simulated with a computer in order to have something, because the only thing we actually measure in the end is what comes out of this detector. But we're interested in, let's say, the small bit here. And to like show this in a more sketchy way, that's what I'm imagining. So you have something like a theory, and the first bit is like the hard process, which I consider as the parton interactions. And then you have this cascade of all the different things going on, like the showering, hadronization, and then the detector effects. And then only at that level, you have RICO, where you do, you actually compare things. So the question is, how do I get from here to here? And all of this bit, I'm not going to talk about today, because they're already complicated on its own, and there are different approaches to just improve detector simulation, which I will also shortly mention on Tuesday. And shower and hadronization are actually super complicated. And well, no, the hadronization is quite complicated because it's purely model-based. There's no fundamental theory behind it. While showering, if you wish, you could incorporate into the hard process. But okay, today I really only want to talk about this first bit, which is the hard process, which seems at a first glance as a solved problem because, well, it's just quantum field theory. You expand it into different orders, and then just calculate it. Well, it is in theory easy, but in practice it's not. Because the problem is, what we actually want to calculate is a physical observable, which means we need a differential or some cross-section, which essentially consists of those different parts. One bit is the PDFs, which is the first problematic thing, because right now we don't have any fundamental description of them. So they're only extracted from experiment, so we only have them available as fitted data. And then we have the matrix elements, which is exactly the core of our physics, let's say quantum field theory part, because that's the thing we can calculate at least a certain level. But if we just think about calculating this at certain orders, at some point we will also be limited. Because for QCD, let's say the frontier right now is next to leading order, but at electro weak, it's already at next to leading order. But the more precision we achieve at experiment, the more precision we also need in the theory in order to match this, in order to get something out of it. So we need this in high precision. I actually also have a paper about this and how you improve this part only. And then you have this very complicated phase space, because in the end, what you have to do is a phase space integral, right? Any observable is essentially solving a phase space integral. And the question is, okay, how do you do this? And the problem is this phase space integral, because of all these different ingredients, cannot be solved analytically. unless you have something very, very simple, like it's written in Pascal and Schroeder, where you, well, just have no PDFs or anything, and then it's easy. But for any, let's say, reasonable, relevant process, you cannot do it. First of all, because of the PDFs, because there's no analytic form. And second of all, because all of the different ingredients and all of the different rich peaking structures and of the high dimensionality. Because often what we consider is 2 to 6, 2 to 7 processes, which means you have like 14, 16, 20 dimensional integrals, and how you solve them.
Sorry.
Sure.
Is there any study for finding the analytic form of PDF?
Well, I mean, yes, there is. The short answer is yes. This means it's like a question of lattice QCD, where how you describe this PDF stuff in like its fundamental form. I mean, to be fair, we're not completely, let's say, agnostic about PDFs. There is some theory knowledge. Once we have, let's say, measured the PDF at a given virtuality like Q squared, we are able to transfer this to a different energy by using RGEs, and it comes under the Alter-Razi-Pazari equations. So you can do this, but the like full full basic thing right now we don't have it. The best hope is lattice QCD because it's a pure soft, non-perturbative thing. But for this, I'm not an expert.
So where are PDFs extracted from? I've always been curious. Because
Where? Well, you do some you do
you
measurements.
can't use the LHC, for example, right? Because you use them as an input.
Well, you can. You just have to be careful that you're not trying to calculate something. So you're not trying to calculate a process from a process where you have extracted information from. Otherwise, you have an overlap.
So are like modern day PDFs all extracted from LHC data? Or
There are kind of overlap. They're measured from LHC data in regions where you know what's going on, where you don't do the actual calculation anymore. And also a lot of stuff from back in the days from lab, HERA and stuff like that at DAISY.
Yeah, so I'm asking about this NNPDF, which is they use neural network.
Yes.
PDF. So can you comment on that?
Yeah, so in principle, they do the same thing, which means they have experimental data and they fit it to getting a PDF form out of it. The only difference to the, let's say, standard approach is that instead of using or assuming a parametric form, which essentially for MSCW, CTAC is essentially a guess. Well, it sounds worse than it is. It's a really good guess. They say like, we don't want to guess this. We just use a neural network, and they try to fit it. So they essentially use just a neural network for a better fitter with using less assumptions in them.
And one more question, like if you go to NNPDF, they have bottom quark and the top quark inside it.
Yes. The
Which
bottom
one?
quark, yes.
And the
Top quark, I don't know.
Yeah, but if you look at CTEC, they do have bottom quark, which is a massive quark, but they don't have the top.
Yeah.
But people often, if you just put NNPDF blindly, if you take the 2070 LSC, they do contribute. Even 40 GB, sometimes people want they contribute. But people question those cross sections, like the convergence of this cross section and how massive quarks.
Yeah, as I said, I'm not an expert on PDF fitting. And I don't think that's an NN, so that's not a neural network problem part. So that's not a problem of the neural network here. It's a problem of your assumption of what do you actually fit. Because this is something which you put in as a physicist that you assume you also can fit a top quark PDF. But of course, that's a huge discussion. You have to be careful about this.
But it did not do that so far. So I'm just saying it's.
Yeah. I think the NN PDF might have a good reason for this, but I would generally say any standard PDF doesn't include a top quark. Let's say most standard is 4 flavor, and already a 5 flavor scheme is already a little bit advanced. But top, well, as I said, I'm not an expert, so don't take me for granted on this, but I think it might not be very sensible, at least not for the LHC, but I might be wrong, so. Okay, so the question is, how do we solve that? And yes, I already said, are there bottlenecks in doing this numerical integrations? And the problem is, yes, there are, because first of all, as I already said, this integration is not feasible analytically. We have high dimensions, and any standard numerical way of doing this usually scale very, very badly with dimension, which means the higher dimension gets, the worse the results gets. Of course, what people are doing is a Monte Carlo integration, which essentially means this best guess we can do is throw random points into your hypercube or in your phase space, and then just evaluate those points at that point with the integrand and take an average of those things. So that's the basic idea of a Monte Carlo integration. And this scales quite well because it only scales, so the dimension doesn't matter, which is a good thing. And it scales with 1 over square root of n, which means if the more points you throw, you will guarantee you get the right result. But this still means that efficiency is a problem, because depending on what integrand you have, the n you have to put in here in order to get a reasonable high precision result might be very, very large. So if this is 1 billion and evaluating 1 point needs a second, you need 1 billion second to calculate something, and that's quite a lot of time, even on a CPU. So you really want to make sure that the number n you have to put in is as low as possible. And here's, for instance, one example where people, and often the problem is when you in the end generate events, you're not just interested in the event with a weight. You want to have it in an unweighted way, which means you kind of reshuffle things such that each event has the same weight and they're distributed according to the integrand you're interested in, because that's the structure in which you can further pipe your events into things like pattern showering, detector simulation. And that's how normal events are working. And starting from this idea, this is the thing of how many times an event gets rejected until it's accepted, just because it's so unlikely to throw it there. And what you could see here for, let's say, just W production, you essentially don't have to use that many trials, so the rejection rate is very, very low. So that's quite okay. But if you just have this very simple process, the more jets you put in, the more and more events while doing this event generation get rejected all the time. So in order to get one event here, you have to essentially redo the same thing 250,000 times, which of course means in the end, if you're interested in 1 million events, you didn't throw 1 million events initially, you actually generated 1 million times 250,000 point events, which makes things even more big and more complicated. So you can see this blows up quite quickly, and if you go to more complicated processes, it becomes even more problematic.
Sorry, would you please explain what is the frequency?
Frequency means how often this appears. So it means for how many different phase space points this is happening, and then number of trials means for those points, how often do you have to throw them on average in order to accept them. So which means the higher this goes, the more points you have to throw this often in order to get accepted, which means this going up is bad. So what you want is that this looks essentially like the red curve. So many points, but all of them are, I don't know, you have to throw them once or twice only.
I
Okay.
understand, yeah.
Okay. So how do we do this? How can we improve things? So that's the standard Monte Carlo integration. And if you're very naive and you, let's say, don't assume anything, the most simple thing you would do, let's assume you have this kind of function, just throw randomly in a uniform way, right? That's without guessing anything. Of course, you can do that, but of course, it's kind of inefficient because you oversample in tails we're not really interested in, which means all of these points you have to throw away, while here in the peak, you're undersampling, which means, oh, here is the interesting bit. So you have to throw essentially twice as many points just to fill up this peak. You see? So, of course, what you can do instead is you use something which is called importance sampling, which means you're not sampling according to a uniform distribution, but according to a different distribution, which, for instance, we call G, which gives you then mathematically this factor f over G. And effectively what it means, you sample more points in regions where the integrand is large and less points in regions where the integrand is small. Makes sense intuitively, I hope. And mathematically, this means if f and g are the same, then in theory that would be 1 and you would only integrate a constant. And of course, then the variance of calculating this is 0 because you cannot, I mean, essentially, if this is a constant, in theory, you only need to throw 1 point to evaluate the integral, right? Because it doesn't matter if it's always the same constant, then it would be perfect. 1 point would be enough. So n is 1. Of course, the more it varies, the more n you need in order to get a precise result. People are doing this. But then often the problem is, like I already indicate here, you have multiple peaks. And sometimes it's difficult to find one of these g's which maps out 2 peaks at the same time. So what people are doing is something which is called a multi-channel approach, which is also the basis of our MadNIS. And this is also right now not machine learning yet. That's like what people are already doing for 20, 30 years. And there you essentially split up your integrand in different regions and saying, okay, here I'm using this PDF mapping only this peak, and then I'm here using a different PDF mapping out this peak. And then you just take the sum of those. And just you need to make sure that the integral sums up to 1. This multi-channel weight alpha needs to sum up to 1 in order to make sure that everything is fine.
So in this case, alpha and g function are assumed by us. Is it correct?
Pardon?
The functions of alpha and g is assumed by us,
Yes.
right?
Yes. So, and what g is normally is essentially, so this is just essentially a function which sums up to 1. And the standard guess people always starting from is saying, let's say I construct 5 channels, then each of the different alphas is 1/5. So you said, you just start by assuming every channel contributes to the same thing. And then from this, you essentially have some very simple approach of saying, I throw 1,000 points, I evaluate my different integrals, and then based on the value of the different integrals, I reweight the alpha contribution, which means integrals which contribute more, like partial integrals which contribute more, get a bigger weight. Makes sense? So that's very simple. The more complicated thing is construct this G where I'm sampling from. Because this means when I want to sample from it, I need some way of making this happen. So what you usually have to do is you start from a uniform distribution. And then for this G, you need something like a quantile function. So you pipe your uniform distribution through it, so you effectively sample according to this function. Which means there's only, like, say, a handful of analytic functions you can construct right now, which are easily invertible. So this needs to be a bijective mapping. And people know some things. So for instance, if you have something like Breit-Wigner, we know how to map out a Breit-Wigner because it's similar to a Cauchy distribution, and the Cauchy distribution we can invert, so that's easy. And this is what people are already doing. So we are not starting from uniform because we know we have peaks. So, and then on top of this basic physics-based mapping, people realized, well, because we have many diagrams, right? And there might be a peak here, but there might be not a peak in this diagram, and also we have interference because you have quantum physics. And in the interference, there might be no peak at all. And in the end, we have the coherent sum of all different channels, which means we have mismatches and something wrong. So what people are doing on top of this purely physics-based inspired is a numerical method, which is called Vegas. It's also very old. It's actually from the 70s. And it's very simple. There you assume that this G, which here I call the P, but it's the same thing, I factorize it, which means I have a different probability in different phase-space directions. So if I have a 10-dimensional thing, I essentially assume that each direction is independent, and I just try to find a better parameterization in this 1D projection, which essentially looks like here. So you essentially try to make smaller bins in regions where you have peaks, and larger bins in regions where you have tails. And if you then keep the probability in all bins the same, this effectively means you throw more points here and less points there. Okay? But this has one problem. Of course, here I'm assuming there are no correlations, which might be a problematic thing because, strictly speaking, that's a very bad guess because most of the time you have correlations. And I already said, in principle, usually starting from this, it's computational cheap. So that's good. So it's fast. But if the dimension is getting very, very high, it converges very, very slowly. But it's also okay because people can help with this because we're not starting from scratch. We have this physical assumption. But the very problematic thing is that we have these phantom peaks. So which means, because we don't take into account any correlations, let's assume we have this 2D distribution where there's a peak here and a peak there. Then what you want is you want to map out this and this peak. Okay. So what Vegas does is it just looks at this projection and this projection. So it's these two peaks in each direction. So it tries to optimize this 1D distribution and this 1D distribution with a grid, and then just overlays this grid. But then effectively means it also creates a peak there, which is not there, and a peak there, which is not there. So effectively oversampling again in regions you're not interested. Okay, that's the starting point, where now machine learning comes into play. So how can we solve that? Of course, you would like to have something which is takes into account any correlations, but how do you construct that? I mean, you need some way of having a starting point which you can also efficiently optimize. And there you can see if you use a neural network, which gives you the freedom of essentially representing this G function. And in machine learning, we have this technique of gradient descent, which essentially gives you a way of minimizing a function, which in our case is the variance. That's because that's the thing we're interested in. So you have a technique in order to find such a function, the very, let's say, with as least assumption as possible. And people are trying this or have been trying this with a standard neural network. So pure basic neural network, which you will also learn probably day one next week, Monday. It's fine because there you can essentially keep all correlations, so you will not have any phantom peaks. The problem is if you just need a neural net, just use a neural network out of the box, it's not guaranteed to be bijective, which means, so this G in this thing is the Jacobian of this mapping you're doing, which means, first of all, the training might be unstable or the Jacobian might even be not well defined. So in the worst case, you have a zero somewhere, which of course is a problematic thing, which means the optimization is very unstable, which we call a training. And of course, because it's Jacobian, we have to calculate like numerically. And if, I will go into detail next week about this again. If you have, let's say, D dimensions, and you have a mapping in D dimensions, in general, what Jacobian of this thing is a D times D dimensional matrix, right? And then the determinant of this thing, because that's the thing which gives you the G or this denominator, goes with order D cube. And that means if the higher dimensions you are, the more expensive this entire thing gets. So that's not very efficient, because then in the end, you're just essentially, yeah, instead of having something inefficient and needing to throw more points, you're having something very inefficient here, where it just takes you so long in order to calculate this Jacobian that you're also not gaining anything. So we need something more fast. So this was in 2017, 2018. And for whatever reason, they did it again in 20, even though we already knew it doesn't work. And then that's the next new thing, which is called a normalizing flow. I just described it very, very briefly, but then in more detail next week, if you're interested in. What a normalizing flow does in a nutshell, it's very simple. It guarantees you that's in bijective mapping. It does it by constructing the network in a certain way, which I'm not going into detail. This means it is a bijective mapping, which means the Jacobian is well defined. And then it also has a very special technique in the way it's constructed that the Jacobians are tractable. Tractable means it's easily computable, because there the Jacobians just go with D. So they grow linearly, which is a huge advantage. So the training, the optimization, and later on, when you actually want to throw points, the evaluation is fast. And what a normalizing flow is essentially doing in a nutshell is, let's assume you start from some latent distribution, so from some Gaussian, and this is the distribution here. It's just a change of coordinates. So if you want to, for instance, describe this new distribution here, which I call P phi, then you essentially just have to evaluate your latent distribution or your uniform distribution times, but because it's log with plus, times the Jacobian of this entire mapping, okay? And essentially, this entire block is the thing you're interested in. So this P is the stuff you want to evaluate. And the nice thing about the normalizing flow is this is the thing you want to put in this F over G thing. So this is G. This you know because it's uniform. That's nice. And this part comes from normalizing flow or from a neural network in a way that it's easy to compute. Perfect. So we have all the gradients and we can calculate this thing in an easy way. And because we don't have any assumption in factorizing, it takes into account all correlations. So we are superior to Vegas. Other questions? If not, you can also ask further or stop me. All right, so this comes now to how does MadNIS actually work and how are we using it? So for MadNIS, as you can see here, it has a lot of ingredients because we started from something very, very simple, which is essentially just this bit. And then at some point realized there's a lot of things already going on and we can optimize at different places. So of course, I'm not gonna directly start with something like buffer training. So I'm first gonna introduce the basic functionalities and explain it on a very simple toy example, which is a 2D thing to make it very easy, very clear. And then based on that, where we know what's going on, I'm gonna tell you a bit more what the problematic things are when you go to LHC stuff. And then I introduce some ways of making things even better. All right, the basic functionality. So as I said, we start from this, also here we start from this multi-channel decomposition, where we have this alpha, which I said, naive guess start from something like 1 over number of channels, and you have this G you want to approximate. And the first thing you do is use physics knowledge to construct those channels and mappings. What do I mean by this? This means that, of course, let's assume I have some process and I have 10 diagrams on a leading order. Then the naive assumption is I construct 10 channels, so 1 channel for each diagram. And then based on this diagram, I construct a mapping G from a physics-based knowledge, which means let's assume I have T2W production with decay in the end. I know there will be peaks in my top quarks, so I already know that I can map these out, right? So this assumption I can use. But then if I look in the total 2 to 4 or 2 to 6 process, there are also a lot of diagrams which are non-resonant. So there I don't have any peaks. So which means for there, I need to start from a different mapping. So that's where I'm starting from. And this is a good thing to see, to use and start from, and you will see later that it actually helps. And then from this, I first use my normalizing flow to refine or improve this G. But then what I can also do, instead of just having this very heuristic way of optimizing these alphas, I can also make these alphas a standard neural network and just optimize them. The only thing I need to make sure is that they sum up to 1, but that's very easy to implement, right? I mean, in some way I can just sum everything and then divide by the sum, and that's it. So this is 2 approaches. And then in the end, I combine these things and update simultaneously the same objective, which in this case is the variance. I want to have as small variance as possible. So that's the idea. Okay. And this is essentially how it's built up. And that's what I already said. So you start from a simple latent space, how you would call it, which is, in our case, a unit hypercube, which then gets mapped through the normalizing flow onto a different unit hypercube. And then on top, there comes this analytic mappings, which are physics-based, which gives you both the phase space momenta X and also the total G here. And then on top, you can use the momenta which you get out here in order to train a neural network on this part to get the alphas. And this you do for all channels. So this is for 1 channel. This you do for all channels simultaneously, which means if you have K channels, you have K normalizing flows, but only 1 neural network for the alphas. Because there, instead of having, because they're connected to each other, you just have a different dimensional output. So if you have K channels, you have a K dimensional output in 1 neural network. And then you sum up everything, your I, and then based on that, you can also calculate the numerical variance of this thing, and this is the thing you optimize.
Sorry, it's a kind of like question. Would you please explain the normalizing floor?
What do you mean?
I don't know what is normalizing flow.
I think I said it 3 slides earlier what it is. I think it's this neural network which remaps
Yeah.
the unit hypercube or some base distribution you know into a different distribution by mappings which are bijective by construction.
So can I imagine this kind of changing variable?
Yeah, it's a change of variables. I think I actually said that. It's a change of variables.
Oh yeah, thank you. I see.
Yeah. But as I said, if you're more interested in just to know how this works, I will give essentially an entire lecture just about that next week. Because they're really cool. Okay. So here's a toy example I considered, which is a 2D thing with this line and this ring. And that's a very nice example. First of all, it's very simple because it's 2D. So I can look at everything at once, which is complicated for LHC examples because if you have something which is 20-dimensional, it's difficult to look at a 20-dimensional distribution at once. You always have to cut out at least 1 or 2D slices, right? So you always lose some information, but if you start with a 2D example, you can just look at everything. And it's also nice to check here because the Vegas would fail. Why? There's no way to construct any kind of axis such that I can align the ring and the line at the same time without like losing correlation. So this thing is highly correlated. So Vegas will completely fail here. It will essentially make a big blob and maybe some blobs here. So it doesn't work. So that's a good starting point for the normalizing flow. Okay. And that's how it looked like. So what we found is at the starting point, we didn't use any channeling. We just used one channel. And we found that the normalizing flow performs okayish, but to be fair, on purpose, just to show that it helps to improve the input, the knowledge input I do, we used a very, very simple normalizing flow. Just to make clear, even if with a very, very small network, you can get way better if you do it smarter. So here, very, very small network. You see, you kind of map out the line, but the ring is not very well modeled. Because again, the normalizing flow is a bijective mapping, and you're starting from something which is here a Gaussian. And the problem is the ring by construction, if you just think about it mathematically, is an object which has 2 holes in it. So it's topologically a different thing than a blob, a Gaussian. And there is a mathematical statement, so you can mathematically prove that it's mathematically not possible with a homeomorphism, which is a bijective mapping, to transform this thing into this object. Yes?
Is this just I mean, you call it a toy example, but is this kind of shape going to appear in the LHC, like a circle and a...
It can, yeah.
What would a circle be corresponding
Well,
to?
maybe not a circle, but maybe something like wiggly or something, and some hype. I mean, you can always probably slice it like this.
Okay.
So you see, okay, I didn't have Vegas in it, but Vegas will perform even worse. But that is the relative error. The moment I go to more channels, I make the life easier because then in principle, I can allow one network, which is essentially split up, just to learn the ring and the other one to learn the line. So here I can see the line is learned very, very nicely. The second flow tries to learn the ring, but here still have the problem that the ring is still kind of problematic because it still has a hole in it. So it's typologically still different from a Gaussian. So you see that the ring is closed here, but here it's open. Because it has to open it, right? Because otherwise you cannot deform it. Which means it looks already way better than this, but it's not optimal. But you can already see the error goes down. But then if you go to 3 channels, then it's easier. Because then essentially, and this is kind of just one shot of examples, how the things are split up happens automatically. Here again, one channel tries to learn the line. This channel learns this bit of the ring. It's fine, topologically also fine. And the other flow learns this one. And then if you combine everything, this looks very, very nicely and the error goes down further. And that's very, very cool. And this was there, essentially we didn't put any knowledge in. So this was pure normalizing flow and based on this channeling. But then we said, of course, let's assume we know something. Let's assume we know that there's a ring, but we don't know anything about the line. So we construct 2 channels. One channel, we start from a ring mapping. We construct a ring mapping. But in order to make at least the normalizing flow learn something, on purpose, I made the mapping for the ring a factor 1000 too broad. So the normalizing flow at least had to learn to narrow it down. And this bit for the ring, which we call overflow channel because we didn't put any information in, we just said, that's some remaining bit, do it yourself. So here you see the ring channel. I still need to exchange this plot, I realized, because we actually had some numerical, some error in the, some bug in the code where this bit here appeared from, and this is gone. So this is just a ring, which looks very nicely. And this is the overflow channel, which perfectly learns the remaining bit on its own. And then if you combine it, it looks much, much nicer than the previous one. And also the relative error goes down. So here you see you have like 0.5, which and the error on the error, if you do it multiple times, is quite big. And then starting from at least knowing something like the ring, this goes down, and also the error on the error goes down, which already tells you on 2D, which is in principle a simple problem, it's helpful to use knowledge if you have it. Yes?
The last time, what is the reason of this decreasing in error? I mean, what is the physical reason for that? Like,
The what?
Physical reason of decreasing the error. In this case, I understand because you already know the shape of the ring. In the second case.
Yes.
But in this case, what is the exact reason for why
Error
does
doesn't
this,
decrease, right? It's the same.
It decreases.
1.3, 1.5, 1.4.
this values are the central values, like 1.17?
Yes.
Oh, I see. You mean, yeah. Well, it has more channels, right? So it has more variables.
Yes.
I don't know.
I don't know.
cannot ask like.
Yes, it's just have more channels, so have more options. And already said that because here you don't have the topology problem anymore, so it's easier. Where here you have it. Or strictly speaking, in order to understand it better, you cannot transform a ball into a donut because it's topologically not the same thing, which is essentially what you try to do here. However, if you have two balls, you can deform one ball into half a donut and the other ball into the other half and just sum them up so that they look like a ring. That's possible. That's why this works way better than just this, essentially. But then again, as I said, if you on top add some knowledge, it gets even better. And what you see here is essentially the weights, the channel weights. Because I said they're between 0 and 1. Here we have two channels, so we only have two of them. And this bit, this blue region, is where this channel is maximum, and the yellow bit is where this channel is maximum. So you really can see that where the ring is, this channel also is big, which makes sense. And there where the ring is, the other channel is maximum. So it nicely distributes the two objects into the different channels. So it really splits it up. Okay? Good. Then, in order to understand some more features, again, I have all of this stuff. I want to explain. I leave out all of this bit because it's not very interesting. I just want to talk about those two things and then show you some LHC examples. The first thing I quickly want to show you is some Vegas initialization. So as I already said in the beginning, Vegas is like the standard approach where you have this factorization. And in principle, it's not a bad idea because it's very, very fast. But the problem is it doesn't contain any correlations. The normalizing flow contains all correlations, but is slow. Okay, that's on a relative scale. It's still quite fast, but compared to Vegas, it's slower. So what we would like to have is kind of combine these things. So that's the idea. So we, instead of completely starting from flow, we use Vegas first as a pre-training, as a starting point, and then only use the flow in order to catch the remaining correlations. So the flow doesn't have to learn everything, which is easy to learn from Vegas. That's the idea.
So sorry, I'm so sorry. What is the meaning of correlation in this table?
The correlation?
How can I understand?
Correlation means that's what I just showed before, right?
Just a linear
Because
length?
there's a correlation. This line and this thing, these two variables are correlated, right?
Yeah.
This is a correlation. That's what I mean. And Vegas cannot catch it, while the flow, it can. But as I said, so the idea is to use best of both worlds. So what we're doing is we're starting from Vegas, doing a little bit of mathematical things, which is not very important, then use this information from the Vegas grid, which is the grid, as a starting point, and then from there we train a flow, which makes everything so much faster and even better, which we will see later, which is a cool thing. So this was one improvement. And the nice thing is, because Vegas just works with bins, so in order to describe, for instance, this mapping, Vegas needs 64 bins, which is actually quite a lot. If you try to describe this in a machine learning way, where you have something better than just a linear spline, you can reduce this actually to just 10 bins, which also is memory-wise more efficient. So which is quite cool. So you actually, even just using the Vegas from a starting point, you can just make Vegas itself faster by using a better parameterization. So instead of having linear splines, you use rational quadratic splines, and then everything fits into smaller memory, which is cool. And this is essentially the starting point then to train. All right, and then again, all of this happens in all blocks. So everywhere, every normalizing flow, as a last layer, I have this Vegas block in it, which essentially now I put in to make things more efficient. All right, other questions on that? I mean, the details are not important, like how is it exactly coded? It's really just the idea. Is the idea clear? Because that's the important thing and the take-home message. The next thing, which I only shortly scratch, is the buffer training. So the problem is, in the training, what usually happens is you have a sample Z, which gets piped through your flow in order to get, in combination with the analytic mapping, to get a phase space point. And this phase space point here gets evaluated at the integrand, and then you get a density, and then together with the integrand, the density, you can evaluate as F over G, and then you can optimize. All good. The problem is, for optimization, I need a lot of points already, which means every time I optimize my neural network, I need to throw points again and again, because every time I need some variable to optimize, I need to go to the sampling, optimizing integrand, and have to repeat it. But first, this can be inefficient for two reasons. First of all, if the flow might be slow, I mean, in principle, you won't avoid it, but this flow might be slow. So you don't constantly want to throw points through it, at least not twice. Second, there might be cases where the integrand is expensive, which can be the case if you have NLO, where the matrix elements can become expensive. So if you have to throw 100 points all the time, then this might be expensive. But we found out you actually don't need, let's say, 1 million points in order to optimize the flow. What is more crucial is that even with less points, that the neural network has chances to see the same points several times to be better optimized. Okay, which means instead of constantly sample a new point and then throw it away, we can keep them in a buffer. That's why it's called buffer training. So we keep this density and this integrand and just iterate the flow over the buffered samples one more time. Because there we already have F and we don't have to evaluate all the time again and again. Which means if this becomes expensive, we save a lot of time, which you can see here. So the training algorithm goes like this. You start generating new samples, train on them, save some bit, and then train on the saved samples, and then you repeat. And then you effectively reduce the statistics because you generate less points in total because you train on the same points over and over again, which means the more often you train, let's say you train 100 epochs, then the pure standard training would be 100 epochs where you constantly generate points, or you say the most crazy version, I just do 1 epoch of generation and then 99 epochs of sampling on the same. Then this R here would be 100. So that's the reduction training statistics. And then the other extreme would be 1. So you can see here, the more I use the points again, and this is the relative change in training time, the more training time I save. And this goes, of course, correlates with the time it takes to evaluate the integrand. So if integrand is very, very cheap, this curve is very flat, but it will also go down somewhere here. But of course, if this becomes expensive and 1 millisecond it's not unrealistic. It's actually, there are situations where this is even too fast. This goes down way, way quicker. So you can already at a factor of 6 gain like 80% of the time, which means it's doing the same thing, but just in a more efficient way, which is also cool because in the end, again, we want to be fast with everything. And then I just show you what's happening if we do this with an LHC example. So the first LHC example we considered was also kind of a toy one, which is a Traillian production with some induced BSM physics where we consider some Z prime, which sits here at 400 GeV. It's not physically well motivated by any means. I mean, what I mean is, it's not like there's a reason why we picked it. The only reason why we picked it is we wanted to have a third peak in our thing, just to test if our multi-channeling works. And what we can first see is that where the peaks are high, so the white line is the truth. So where we have high statistics, our normalizing flow, which is everything in colored, matches the truth very, very well, which is what we expect because there we have high statistics. So it fits very well to everything. Here are the tails. There we have some discrepancy, but that's also expected. If you have less points, then the optimization gets worse. We can also see that each peak, the normal Z peak, the Z prime peak, and if you wish, the gamma peak, which is continuum, are mapped out individually by each channel. That's also nice. So each channel takes care of one of the peaks. And then here you can also see the channel weights, which also makes sense. So that's, I mean, in a way, that's the way we expected it to be, but it's always good to make this test to be sure that everything behaves the way you expect it. Here you can see where the blue peak is big, there also the alpha channel is essentially 1 and the other channels don't contribute, which is what you expect, but it also makes sense and you can see it's actually the case. And these channel weights are learned by a neural network because you can see they're everything, but they're not all at 1/3, which I said is the naive assumption. The naive assumption, the starting point, everything is 1/3 and they're all the same, but they're nicely adapted such that where blue is relevant, this blue channel gets big, etc.
So is this 3 dimensions because of the gamma, Z, and Z prime? Like,
What do you mean 3 dimensions?
because before you had like a 2-dimensional plot, right? Your toy model.
Well, no, this is
Like how many variables do
E
you?
plus E minus is 2 particle final state, which means 3n minus 2, 3 times 2 is 6, 4 dimensions.
I see.
But this is of course a 1D projection. I just looked now at this ME plus E minus.
I see.
I mean, here I just randomly picked one observable to show you because again, for 4 dimensions, I don't know how to show 4 dimensions. I
understand. So
but,
the dimensionality of each process is just determined by the final state.
Exactly.
I see. I see.
Yes.
Okay.
And this is one of the possible observables you can look at. There are more in the paper. But it already gives the main story. That's the important thing. And then we also checked what's happening if we use this buffer training. So this central line gives you the full sample training where you have more statistics. So you would expect having more statistics is a principle better. And then all these the other 2 lines are belonging to a reduction of statistic by factor 3 and 4. And then if you do this multiple times, you get a fluctuation. You can see that within this fluctuation of multiple trainings, everything are compatible with each other. So everything is within 1 sigma, which means you can safely use, let's say, a reduction of statistic of 5 and still get a very precise calculation, but save time without worrying of losing precision, which is the important thing here. Okay. Then, because things are not always as simple, and a lot of things on this things I'm gonna explain, we also looked into more complicated stuff. Here we looked into some VBS, let's say vector boson scattering. Here we already have 4 particles in the final state, which again means 3 times 4 is 12 minus 2 is a 10-dimensional phase space. That's why here I neglected showing you a 1D distribution. I just decided to show you, first of all, the relative error and then the unweighting efficiency, which again is the thing I mentioned in the beginning, the probability to accept or reject the event. And the higher this is, the better. And here it's the other way around. The smaller the relative error is, the better. And here in the first line, you see Vegas. This is the Vegas thing. And these are different incarnations, which I will also talk about in a bit, of MadNIS. And you can see that this unweighting efficiency, which is around 1, is a factor of 9 worse than all the MadNIS incarnations. And also this error is way higher than this. So you can see that you already get an improvement by a factor of 9, but instead of using Vegas, using MadNIS, which is quite a lot. So a factor of 9 effectively means a factor of 9 less computing time. So instead of calculating something for 9 months, it only takes 1 month for the cluster. Then you can also look into more in detail among. So this is essentially the same plot, but I just cut out the Vegas bit because then I can look into more details about the different versions here. And there you can see that if I use this Vegas initialization, which I showed you before, so using the smartness of Vegas combined with MadNIS, so where you only have to learn the difference, helps. So this is without this, and this is with it, so you can get some improvement, and also the error goes down quite a lot. Then fixed and trained alpha is exactly what it means, what it is. So I'm either keeping the alpha fixed at the good physical guess, or I'm optimizing it on the way. And for this specific process, it's doing something which you can see here. So you really can see that if I'm starting from this fixed guess, which is not 1/3 here, it's based on some other stuff. But then if you go down, it actually improves. Which in this specific case, it's actually not highly non-trivial, because this exactly means, so the standard guess here is based on the assumption that if you have 10 channels, that essentially only all squared of each channel contribute. Based on this assumption that this is true, you know what I mean? If you don't know what I mean, I can also draw it somewhere.
Maybe on the black.
Maybe on the blackboard so that everybody else can see it. So let's assume you have some matrix, which is M1 plus Mn. Here we go. Then, of course, what goes into the integral is m squared, right? So you have m1 squared plus all the squares, but of course you also have all the different combinations of the interferences. So the standard construction of these alphas are based on that this part essentially is neglectable and only these parts contribute. Meaning, if this is negligible, which is true for some cases, the starting point is actually very, very good, which you will see in the next plot. But in VBS, that's why this goes down here, these interferences are important, which means the alphas, starting from the assumption that this is unimportant, of course, are not optimal. But then, because we have a neural network, we can optimize the alphas such that it tries to take these stuff into account, which would not be possible actually with our neural network, because there's no way, if you sit down, do all the math, to get these guys into your object. Okay. Let's turn it off again. This was this thing, right? Perfect. So this is highly non-trivial, but this also means that our optimization works, which is cool. And then we also see that the buffer training only has a small effect on the performance, and within the error bars, it's compatible, which is fine. Okay, and now we also looked at a little bit simpler process, which is W plus 2 jets, which was also on this plot right in the beginning, if you remember, with W plus multiple jets, which means it's a critical one. Here, you also get even a factor improvement of a factor of 14, which is really much. But there you can see that going from here to here, which essentially like starting from this physical guess or train alpha, essentially doesn't make any difference. which is exactly here the case that for this specific case, the interferences are small. So this physical assumption that the differences are small is correct. And if the assumption is correct, then there's no need for the neural network to optimize it. Or it probably tries to, but then it sees, oh, it's already optimal. So this doesn't make anything. Which is also something we expected for that process. But again, it's good if all of the thing which is complicated and intertwined also gives us back what we expect. Because in the end, at this point, we were still at the, let's say, proof of concept level where we need to check that everything works and behaves correctly. And otherwise, except for this specific thing, it's very similar to the VBS thing. All right. This brings me to the end, my summary and my outlook. So what I showed you in the beginning was why, first of all, machine learning is relevant, or why it could be relevant, even for us theorists. And I showed you that MadNIS really outperforms. We get a factor of 10 or 14 compared to current sampling methods. So that's really up to date what's actually used right now. And we saw that, I showed you in the toy model, that using a multi-channel is more efficient, also when trained simultaneously with the flow. And that starting with Vegas initialization and using physics knowledge gives a big improvement. That's really critical. And as an outlook, which is something I'm essentially currently working on, well, not right now, but otherwise, is fully integrate MadNIS into MadGraph. I'm not sure if you know MadGraph, depending on what your physics work is, but MadGraph is essentially one of the 3 big softwares which are used by experimentalists in order to get their Monte Carlo simulations for the experimental analysis. So MadGraph is like one of the 3 big shots. The other ones are Sherpa and Herwig with your stuff. So it's very important that we get this into it, hopefully before high Lumi LHC starts, so experimentalists can actually use this. But that's like one thing. The MadGraph people want MadNIS into MadGraph, but what I also want, because I'm the, let's say, author of MadNIS, I still want to have it in a modular form, which means I still want to have MadNIS as an individual package, which means anybody else who's interested, not just integrating phase-space integrals within MadGraph, but for any kind of integrals, because MadNIS in its basic core, just a very good object to get integrals faster numerically. So if anybody else wants to use it, I still want to say, yeah, here's MadNIS. So I say I want to fully integrate it, means I want to be able to use MadNIS in MadGraph out of the box, but I want to still keep it separate. So MadNIS is still a long thing. And of course, we keep on want to test performance on more stuff, like even more legs, like 2 to 6. We also want to try to check next to leading order stuff, because that's something we did not check yet at all. And there things can become more complicated, because at next to leading order, you might also have problems with divergences. And another thing we need to check is what's happening with complicated cut structures. Because obviously, if I map out something which is very smooth, all is good, but cuts give me very hard cuts in my phase space, which might be more complicated. And this is very relevant because everything at LHC is always a very, let's say, restricted phase space, because that's what's given by the detector, right? So we know we only can measure up a certain PT or a certain eta, and we have to cut that out. And then my dream goal is that at some point, everything in the simulation chain, or at least parts of these, are individually able to run on a GPU, because GPUs are much, much faster than CPUs. And what also would be nice in this context is if everything is differentiable, because it would also help to make the optimization step even better. This is our logo, and this is how I foresee when MadGraph goes machine learning. So this is the MadGraph logo, and the other bits are the neural network parts. And if you're interested in how machine learning might be applicable for your topic, there's this really nice website which is called hep-ph Living Review, where this is the, let's say, outdated version. And I just recently got a facelift, which now is easier to digest, where we have different categories from classification, regression, symbolic regression, dark matter studies, everything is in there. And so if you're interested, if anybody in your topic has already might be used machine learning, it's very nice to check out this website and have a look. Maybe there's something in for you. And that's essentially where I would like to stop. But of course, if there are any further things you're interested in or want to discuss, I'm happy to answer more questions. Otherwise, I'm ready. Done.
Thanks for a very nice, interesting talk. Anyone has a question?
This is the other kind of biggest program like Calculator, which is also kind of a generator.
Sorry, can you?
There is a program called Calculate, which is written in C,
Okay.
which also uses Vegas routine generator.
Okay.
It's not as efficient as MadNIS.
Yeah.
So when you go to 2 to 3, it's okay, or 2 to 4, it's not so good.
Okay.
But can it be implemented there also?
Sure.
But do you have language preference or?
Well, it doesn't matter. I mean, this MadNIS itself is written in Python, but there are easy Python tools that does bindings. So MadGraph is actually written, that's the worst. MadGraph is written in Fortran, and we use it with Fortran. So that's not a problem. So yes, that should work. I don't know this tool you mentioned. I don't know all of them.
Yeah, it's a very good tool, it's a Russian collaboration.
Ah, that's why I don't know. Yes.
Other question?
So you said you want to integrate MadNIS into MapGraph before HiLumen, but isn't that many years away?
Well,
Is it going to take a very long time to do this, or?
I don't know. Halloumi is not that many years ago, right? Not that far away, I would
Isn't
say.
it 28 or maybe that's too?
28, I thought it's earlier, but maybe I'm wrong.
Is it next year or something?
It's sooner than we always think.
I see.
I don't have the right timeline right now. I thought it's 20. I thought it's 25. Maybe I'm wrong.
25.
Maybe I'm wrong here.
Oh,
I need to
okay.
check it actually. But at least we're currently, let's say, coding like burning because we think it's faster than we expect,
Okay.
and also we want to get it out.
Sure.
In principle, it's already working, which means if you go on the GitHub website and download MadGraph, there's already a binding to MadNIS, and if you download both, you can use it. But what I mean is fully integrated. I want to make it easier for the user. So in a way, when he just runs the process, it automatically either starts or doesn't start MadNIS, because there's also cases where pure Vegas is fine, and it's just an overkill on top to train the neural network. And then essentially based on different parameters, like how many events I want to generate or how complicated is the process, this is either per default on or off, or of course I allow the user to use it if they want. So that would be my dream goal, and we're currently working on that.
Parallel computing or CD?
Yeah, sure. Yeah, that's the nice thing about the multi-channeling actually, is that in principle, each of these channels, which you can have quite a lot for complicated process, can be completely independently sent on a cluster. And even those then, and if you then each of these put on a GPU, you would be super fast. So GPU is even better than having parallel CPU computing. Because in principle, one GPU has like order 1,000 cores or even more. Which of course also comes with problems, because this only efficiently works if everything is parallelized in the code, or let's say vectorized, which most of the old code is not. For our stuff it is, but standard MadGraph was not vectorized because they didn't have to. But now, because they want to put things on a GPU, and also for our binding here, they started to vectorize it. Or let's see, it's pseudo-vectorized, I would say. And then, yeah, things are faster. But that's like a thing. We have like it's not just one construction site, like just a MadNIS thing, and then everything I do in MadNIS is done, we can use it. It's also a lot of work in parallel, which is happening on MadGraph, getting things on a GPU, running matrix elements faster. So for instance, at some point, they put a matrix element on a GPU because the matrix element was actually the bottleneck in the entire calculation. And now the matrix elements are faster by a factor of, I don't know, 100. And now the bottleneck is the PDF. And which is kind of in a one way, a nice thing because it already tells you, oh, cool, we put a lot of effort in it. And well, the phase space is also not very fast, but this will improve with MadNIS. But then the problem is the PDF. Right now, we cannot do anything about it because that's something external. Because this that's nothing MadGraph does. We also get it from a software package, which is LHA PDF. And apparently, they're working on that too. So the dream goal is all of that gets optimized and then we're faster. So we can cope with the much more data we expect at high-level LHC. At least at that level, of course. Then there's still hadronization and detector level. But that's an entire talk on its own. It's going on there. But in principle, there's a lot of people working on all the different things. And I also feel like, I mean, of course, I'm not that old, but I feel like in at least last 5 to 6 years, I feel like more and more collaboration between theory and experiment got better, like it was 10 years ago, where I always felt like, yeah, theorists are doing their stuff, and experimentists doing their stuff, not really talking often. And now realizing, okay, obviously we found the Higgs, but Susie was not there. So all the low-hanging fruits are gone in a way. We need to have high precision, both in experiment and theory, in order to find maybe small deviations somewhere in the tails. They realized, well, maybe it's a better idea to communicate exactly what we need as theorists from them and vice versa to push that further. So I think that collaboration got better, at least my impression. I don't know how it is here, but at least in Europe it's the case.
So in MadNIS, is there any specific physics channels that would, like, let's just say they had 2 channels that have the same number of final states, but if they have different particles, would there be any difference in like W bosons would do better than quark? Is there any at like the choice of standard model particles? Is it all identical? It just depends on the number of final state particles, or would there be specific processes that work better than others?
Yeah. I mean, of course, it makes a difference even in a standard model. I mean, if you have just QCD, there's not so much going on in a way because there are not so many resonance things going on.
Right.
While if you have electroweak stuff with a lot of W, Higgs, Z, you have all the different particles, all have different masses, so you have different peaks in different regions.
I see.
And they're all connected. So everything with electroweak, that's why I showed you this VBS example, because there you have peaking Ws. These are more complicated. Especially, and this was even a simple case because we had stable Ws, but all of you know a stable W is not real life. In nature, they decay. So the true answer would be decaying both Ws, then you have 2, 4, 6 final state. And then it gets even bigger. And then within this 6 final state, you have these 2 Ws which become on-shell, but then you have all these diagrams where you can have the same final state, but with all the Ws in it, which are completely different topologically. And then you have to find a way of describe both things equally good, which is a non-trivial task. And at NLO, it becomes even more complicated because then you have loops and their divergency, which you can, of course, I mean, if people just calculate, that's in one way very satisfying, but also in another way very not very helpful. Is if you calculate just amplitudes, it's a nice thing, it's cool, but then you realize, okay, you have within your amplitudes, you have different kind of divergencies, right? You have ultraviolet divergencies, which we know of, which is essentially comes with, which you can regularize, which is fine. But then you also have infrared divergencies, which you usually don't care about if you just consider the amplitude itself, or you just do the statement, yeah, I know they are there, but I can mathematically prove the infrared divergences in a virtual loop cancels out with the corresponding real amplitude. Perfect. But numerically, it doesn't help me this because I have one object, which is a virtual amplitude, which lives on d dimensions. And then I have a real amplitude, which lives on d plus 1 dimensions, which means the cancellation I cannot do on integrand level because they are not in the same integral. Which means I have something divergent here and I have something divergent here, which I have to integrate numerically. I know they should cancel, but, well, even though mathematically I know infinity minus infinity is fine, it's numerically not well defined. So I need to use a lot of numerical techniques in order to cancel those divergences locally and make things fine, which makes the integrand even more complicated, which means the phase space integral becomes more involved, and et cetera, et cetera. So there's a lot of things you have to keep in mind. Yeah. So there are different level of complications, higher orders or more lax.
Personally, I think your talk was very fantastic to me because your explanation was very smooth. But since I'm not good at machine learning, so I don't have any question. Yeah.
Yeah. It's. I mean, in a way, it's very machine learning loaded, which of course, because that's what's in it, I cannot remove it. On the other hand, it's also try to link it that it's very relevant to actual thing.
By the way, if you succeed to make us to use MadNIS in MadGraph, then when we use MadNIS, we don't need to know the algorithm.
No.
Yeah, right. Just
Not really, yeah.
Yeah.
I mean, for the let's say, I mean, that's why we call it an RP, right? That's what the RP is. You have one hand the expert, and then in the other end of the RP, there's the dummy user, which just is happy that it works. But that's also why we do a lot of benchmarking and testing and test if it actually behaves as we expect, which we just naively look at it, as I said, in different plots, like, okay, yeah, it peaks where the peak is. Yeah, sure. I mean, that's fine. But that is actually true. I mean, maybe I'm more excited about it because I have to code it, but then it also like means it actually works the way you was expected. If it would behave differently, then means there's something fishy going on. So that's always good in either way to have these kind of checks and these kind of, let's say, trivial, let's say, they seem to be trivial, but they're not necessarily trivial in this high dimensional thing where you not really know where the optimization goes. Which is generally a problem in machine learning, and which we'll also talk about next week in school, probably quite often, that you have all of these complicated structures which are highly nonlinear, and you do some optimization, and you're sometimes not really sure if it's behaving exactly the way you expect it, right? Because in a way, there's this funny meme somewhere, someone throwing, let's say, garbage into a neural network. You cannot expect that something useful comes out of it. So you always have to be careful of what you're doing, which is generally true for each numerical method. And funnily enough, people doing normal fitting or normal analysis do this. But then, I'm not telling any names, but then there are, of course, people out there thinking, oh, it's a neural network, I don't have to think, which is not true. You still have to think what you put in and be aware of what you're doing. And then it also gives you right results. Of course, if you misuse it, this is something I sometimes confront with some people completely misusing the tool because they, as I said, throw garbage in and expect something magically coming out. Then they get also garbage out, telling me, you see, it doesn't work. And then you have to explain them, well, the problem is not the tool, the problem is the user. So, yeah, you always have to be careful.
Okay, thanks to the speaker again. Thank you so much.
Welcome.
We have a seminar leader who will join us. I think
everybody, right? Or
What time will it be?
no, maybe 6 o'clock. I don't know.
Fine. I'm very.
Most
Do you
will
have any
tell you.
preferences?
I got the same question already. I don't really mind. Like,
Yeah. I can give you some options to pick